Good morning or afternoon, everybody, depending where you are in Canada today. So we're going to get started with our webinar today on getting started with SOLIDWORKS simulation. And really, this is about your first simulation. If it's something you've always wanted to try or something you've tried maybe and then went, wow, there's a bunch of features, I really don't know what these do or how to set them up, you're in the right place. Today, we're going to run through the basics of simulation and also get some examples going and then show you guys some live setup on some parts. And I'll actually make those parts available to you at the end of the webinar as well. And we'll talk about this more at the end. But what we'll do, I'll probably put those files into a Dropbox, and then we'll share that download link with everybody who has attended today. So. Again, welcome guys. My name's Peter Chalboden. I'm the Simulation Product Manager at Javelin, and we're here to talk about getting started with SOLIDWORKS simulation. So I'll turn the webcam off so you guys can focus on the screen. Nobody needs to see my face anyways. And we'll get right to it. So we'll run through talking about your first simulation and some questions you may have. We'll talk about the basics of simulation, what you need to know and why it would be, what things are important, what things aren't. We'll talk about the setup of a simulation study, talk about how to solve it, and then the important part, we're going to talk about viewing results of those studies. So, it's your first simulation. You probably have a lot of questions if you're just getting into simulation or if you've tried some yourself and then never had any formal training on it. So you wonder, how do I get started? What are all these options? How do I need to set it up? And then the crucial one where I find most of our customers or most of our people have issues with simulation, or not issues, but uncertainty, is how do I know if I did it right? How do I know if these numbers are something I can trust? Well, it's not supposed to be hard, guys, and once you actually learn about it, it's not hard. It's actually very, very easy, and it's just repeatable steps that you're going to do every time. So what isn't simulation? Well, it's not magic at all. A lot of people go, oh, wow, it's fancy. It tells me how my part's going to behave. Well, it's just like any other piece of software. There's no magic going on behind the scenes. You need to follow specific steps to produce desired, repeatable results. Simulation's not a mind reader. It's not going to do anything unless you tell it to. So don't assume that just because you know how the part's going to behave, that simulation does. You really need to tell it exactly what you want to do. So another tip I'll mention here, don't shoot for 99.9999% accuracy. And we get customers that will email us and go, oh, wow, when I change my mesh here, my stress changes 0.001 MPa and it's not stabilizing. Well, don't try and get it down to that nth degree of accuracy, because you're only as accurate as your material inputs. How accurate are your material properties? How accurate are you with your loads? Is there any uncertainty into how those loads may change? Usually what we find between material deviations, load uncertainty, etc., there's usually a good 5 or 10% uncertainty in your inputs. So there's no point trying to get the simulation solution down to the last decimal place if you've got a 10% variation on the inputs. Same thing as any other software, guys. It's garbage in, garbage out. So use that. The inputs can be a really good realm of how accurate you really want to make your simulation. So, the basics. What we're going to do in a simulation study, if you guys haven't done this before, there's basically a series of steps to go from what we have on the left, the CAD model, to what we have on the right, a final stress result we can actually look at. So, to start with, we might simplify the geometry. Now, that's getting less and less necessary as computing power grows and grows. I have more computing power on my laptop now than you did on a big mainframe workstation 15 years ago. So, but there are things we may do, things like engraving. If you have company logos engraved on your part or tiny little embossed features and things like that, get rid of them. They're not really going to affect the stress result, but they will be very hard to mesh and control the stress around. So, tiny little features, get them out. Then we'll start with the actual setup of the model, and this is what we call pre-processing, sort of everything before we hit the solve button. We need to give SOLIDWORKS some steps, and we'll go through this again in a moment, but you need to tell it what type of analysis you're doing. Are we trying static or buckling or thermal, etc.? We need to tell it what materials we're using, so it knows how strong and how stiff the materials are, how they'll behave. Then we need to talk about our loads and support. So how are we fixing the model or restraining it? And then what are we doing to introduce load? Is it pressure? Is it force? Is it a torque, etc.? Well, once that's done, the last step is mesh the model. And that's where we break it into these thousands of tiny little elements. And it's actually where the term finite element analysis comes from. We're taking continuous geometry and breaking it down into thousands of little finite elements or pieces. Those pieces are very easy for the computer to numerically solve the stiffness and displacement of. Well, once we have that mesh, we click the run button. It runs for a little bit. That could be anywhere from 5 seconds to a couple hours, depending on what solution you're trying to run. And then we're going to get some results. And we'll show you guys today what we can do with those results, how to interrogate them and look at them, and limitations you have to keep in mind. So to start with, we'll go over the element types in SOLIDWORKS. Now, the most common type of element you'll see is the one we have on the left. It's solid elements. These are the default element type for anything in SOLIDWORKS. And what these are, they're triangular pyramid-shaped icons or elements, what we call a tetrahedral shape. They're very good for most chunky parts and as a default, but they get limited when you get into very thin parts. Now, when you get into thin parts, you'd need so many solid elements through the thickness of the parts, it would just end up with element overload. So we actually have specific two-dimensional elements for things like sheet metal, plate steel, thin-walled parts. And they're very good for analyzing things that are thin, whether it's sheet metal, plate steel, pipes, etc. You'll notice if you ever start a model in SOLIDWORKS with the sheet metal functionality, if you ever try and analyze a sheet metal part, it's going to analyze as shells by default. We also have beam elements, one-dimensional wireframe elements, and they're very simple, but they're very fast. You can analyze very large, very complex frame structures very quickly with them, and those are actually the defaults for weldments. If you analyze a weldment structure, unless you tell SOLIDWORKS otherwise, it will treat it as a beam structure. So there's all these different element types, but today we're going to focus on solid elements. They're the most common, and they're going to be the first ones you use if you're just getting started in simulation. So, a little bit of terminology before we go. I talked about elements, and when we talk about elements, these are the actual pieces we're breaking the part down into, and you'll see a picture of that over on the right side. The nodes are the points where the elements actually connect together. So if I had, and I'm going to draw this just in 2D, but if I had a bunch of triangular elements here touching, well, those are elements. The nodes are the corners of them. So anywhere you see sort of an intersection point in here, those are all nodes between my elements. Let me clear that drawing for a second. And there we go. So the one final thing I'll mention, you'll hear me refer to mesh, meshing the model, creating a mesh, refining a mesh. Well, mesh is the term we use to collectively describe the collection of elements and nodes in the model. So when we mesh a model, using it as a verb, we're talking about creating the elements out of it. If we're talking about, well, show the mesh, I'm talking about showing what we're seeing right here, show the representation of the mesh. If I talk about refining the mesh, I'm talking about making it smaller or more detailed in some areas. So with that basic terminology, we can move forward. Now, the setup of a simulation study. Really, we're going to talk about the different things to set up here, but again, it's not magic. If you follow the same steps from start to finish on every model, we will get the same kind of results. So when we start a new simulation study, and you'll see that in a second, it splits our design tree in two. We get this new little simulation tree over on the left-hand side of the screen, and what we need to do is work from the top of that tree down to the bottom. And there's four main things we need to do there. To start with, the parts folder or parts icon. If you just have one part, well, this is where we define the materials and the element definitions, so solids, shells, beams, etc. And what are all the parts made of? Connections is the next one down. Well, with single parts, you don't need to worry about this, but when you get into multiple parts, and we'll look at an example a little bit later, we need to tell SOLIDWORKS how those parts interact. Are they bonded together? Are they free to slide and react off each other and develop contact patches, etc.? So that's what we set in the connections folder. The fixtures and loads are the next two icons you'll see, and collectively, these are referred to as boundary conditions. And you'll hear that term thrown around a lot in FEA. They're called boundary conditions because it's basically the conditions we're applying at the boundaries or the exterior of the model. Now, boundary conditions sounds a little intimidating if you don't know what they are. It sounds complicated. It's not. It's just a term for fixtures and loads. How are we holding the model and how are we loading the model? So, final step will be meshing. And breaking your part down into thousands of tiny little pieces sounds like it's going to be a complicated thing to do. Luckily, SOLIDWORKS has one of the nicest, most automated meshers in the industry. We actually have a few of the best, most automated meshers in the industry. So we'll talk about that, but this mesh icon is where we go to control, to create the initial mesh, and then also to control it later on. Now, everything in this menu is right-click based, and we'll see that in a moment. So again, remember to work from top to bottom, and we'll go. Now, just a couple guidelines as we go. I'll come back to this in a second. So why don't we actually leave this on presentation mode, and I'm just going to switch over to SOLIDWORKS. So what we have here is a simple part, and I'm just going to turn off some of my toolbars there. Simple part, we're in part mode right now, and this is just a single feature extrusion, guys. Doesn't get much simpler than this. Now, we can complicate it, but we're going to pick a model like this to work with because it's nice and simple in a single part for a first run. So, first thing you'll need to do is make sure your simulation add-in is turned on. If you see the little simulation tab here, your sim add-in is turned on. But if not, you'll have to go over to the add-ins tab on your command manager and just turn on your simulation add-in. Give it a couple of seconds. It may prompt you to activate it if it's the first time you've turned it on, and then you'll see this little simulation button pop up. So how do we get started? Well, we're going to go to the simulation tab, and we're going to hit the new study button. So when I click this, I get a bunch of different study types showing up in here. Static, thermal, frequency. Well, it really depends on which package of simulation you have. You might just see static, you might see all of these, but static is the type of analysis we're going to start with. And what that means, guys, a static analysis is one with non-moving loads. We're assuming the loads are applied slowly in here. We're not doing impacts or vibrations or anything where we've got really fast movement. We're just trying to apply loads slowly and see how the part reacts. So we can give this a name, and I'm going to call this a first try, and I'm going to click the OK button. So you'll see now it's split my tree into two. I have my part tree at the top, I have my simulation tree down at the bottom, and it started a new study tab right down here where it says first try. So you'll see I can actually edit my model and do things right now, but if I ever want to get out of simulation mode, I just switch back to my model tab and I can make changes to the model, etc. Then when it's ready to go back to simulation, switch back to the simulation tab. So let's talk about what we mentioned here, guys. What was the overall theme? We're going to work this tree from the top to the bottom. So let's do that. First thing, our part. Now, it's called T-bracket. That's just the name of the part. I need to apply material. So I'm going to right-click and just click the very first option there, Apply Edit Material. So when we get into this part, you'll see there's a default material here called alloy steel, which is just the SOLIDWORKS default steel, but we've got various different steels, various different aluminums, various other materials in here as well. And you can also create your own. I'm going to stick with, why don't we go for a 6061 aluminum. In this case, I'll grab my 6061 alloy in here and click Apply. But you'll notice in the mechanical properties window here, we have 4 properties that are highlighted in red. Those are actually the only 4 numbers we need to create a new material in a static study. So what those are, there's the elastic modulus, or the stiffness of the part. There's the yield strength, or the strength where your part starts permanently deforming or yielding. Poisson's ratio, that describes how when we stretch a material in one direction, what happens in the other direction, the cross direction, and then density. So these are 4 pretty easy properties to find. Just a quick Google search or a phone call to a material supplier or a data sheet is going to get you these. You can create any material you want to with these 4 numbers in about 30 seconds, but it's not something we're going to do today. So once I've applied the material, I click the close button, and I'll see right here, I've got a big check mark in front of the part box, and it shows me my material. Well, that's done. So we're going to keep moving down the tree. Now, connections. Well, connections are how parts interact. And because we have one part, we can skip right over the connections folder. Now, we'll go down to fixtures. Fixtures and loads, again, those are my boundary conditions. I'm going to tell SOLIDWORKS how we're holding this part down in my fixtures. So when I right-click, I'll see my options. And the simplest one is a fixed geometry restraint. Looks like an anchor because it holds the part down. It holds whatever faces or edges I pick, just solid. But we also have other options. Roller connections that allow things to, it'll stop them from moving in one direction. Like, for instance, it'd stop something from diving through the floor, but it'll still allow it to slide or skate along the surface of the floor. Hinge connections to simulate hinges, and then other things, bearing supports, or bearing fixtures, foundation bolts, etc. But let's stay simple. We'll start with the fixed restraint. So when I see my fixture window, I'll see a nice little animation of what this fixture does. So fixed, mentioned that roller connection, there you go. It's going to stop it from moving off the plane, but it'll allow it to skate around the plane. Or hinge connections. I'm going to go fixed, and I'm just going to say, let's fix the very top of this part. Now, when I click OK, it's going to do that. You'll see these little green symbols pop up. That's the symbols for the fixture itself, and showing us the degrees of freedom it's restrained in. The next step of this is going to be applying loads, and I'm just realizing I haven't told you guys what I want to do with this part. I would like to apply 300 pounds of load to each of these little side faces here. So I'd like to simulate pushing downwards on this face and pushing downwards on this face with 300 pounds each. So how do we do it? Well, I'm going to go to my loads folder, and again, I'm going to right click. So when I do that, just like we saw with fixtures, all my options pop up here. So forces, torques, pressures, gravity, centrifugal loading, hole bearing loads, etc. We're going to stay simple again. Let's use a force. So what I get to do here, I get to choose which faces or edges or points I'd like to apply the force to, and typically I'll use faces for that, and I'll show you guys what I mean. So I'll go over and I'll select this face. I'll also go over and select this face. So the default is what we call a normal force, a force pushing directly perpendicular or normal the face, but it doesn't have to be. If I'd like to change that one direction or another, I can actually go to the selected direction box, then pick any edge or sketch line or even a plane for direction. So if I wanted that going side to side, I could grab this edge right here, and suddenly I have a side to side load. But let's go back to normal. Well, I said I wanted to have 300 pounds on each face. Well, right now it's dealing with newtons, and I'm fine with metric or imperial, but I said 300 pounds. Let's switch it to imperial. We can work in whatever units you'd like, and you can switch back and forth multiple times in the same study. So I'm going to go down and I'll say 300 pounds. And you have to remember this one little box underneath the load setting, per item or total. Per item, it's going to apply that load, 300 pounds, to each selection that I've made. If I go total, it's actually going to distribute it equally over those faces that I've selected. So we'll go 300 pounds per item. Okay. Well, we're done a lot of that study. Guys, we've worked down the tree, and the last thing after my fixtures and loads is meshing the model. So let's talk about that, and to be honest, we could do a series of webinars on meshing, but I'm going to show you guys some of the easiest ways to mesh today. So I'm going to right click on the mesh, and you'll see a bunch of options here, but the one you want to go to is create mesh. So it brings up this little slider bar window here, and at first glance you just see a slider bar from course to fine, but if you pop open this mesh parameters box, you'll actually see we've got a bunch of different meshing options here. What we call the standard mesher, curvature-based mesher, and the blended curvature-based mesher. Well, what I'm going to do, I'm going to start with, I would honestly recommend usually using the curvature-based or the blended curvature-based mesher, and I might actually just click OK and see what this looks like as a default mesh. So I click OK. This is what it looks like. It took a couple seconds there and my screen flashed, but it's gone in and meshed the part. What that curvature-based mesher will do, it's automatically refining around fillets, around curvature regions, places I'm going to need a finer mesh. Now, We'll talk more about results in a moment, but this does not really look like a refined enough mesh to me. And well, there's ways we can troubleshoot this, but really you need at a minimum at least a couple of elements, 2 elements going through the thickness of the part. In some areas in here where we have 2 elements through the thickness, well, that works, but over here we just have 1 element spanning the whole thickness. I'm going to try and make this a little bit finer. So I'm going to go to my mesh, create mesh one more time. I'm going to drag this down towards the fine side a little bit and click OK. Keeps flipping back to my PowerPoint there, and might actually do it one more time. We're going to go all the way to fine and see what happens. There we go. So I've got at least a couple elements through the thickness everywhere in here. That's good enough for me right now, and it's time to solve the study. Sorry about that, guys. If you heard it, I just knocked a glass of water off my desk. So what are we going to do? Before we actually click solve, there are some options we can set up, and I'll just show you guys. If you right-click on the very top level study there, and you go into properties, we're going to see the study properties here. And you know, before we even jump into that, let me jump back to the PowerPoint for a second. Well, there's a couple things I'd like to mention. So again, with the mesh, start simple. As I mentioned, don't try and get the be-all, end-all mesh on your first try. And then we'll come back after we actually look at the results, and we'll talk about where we need to refine the mesh afterwards. And it's typically in those high-stress regions. Now, when we get into solving, which is what I'm talking about here, and we go into our study properties, there's actually a few different solvers we can choose from, and if you're new to it, you won't have any idea what they are. FFE+, Intel Direct Sparse, Direct Sparse, what do you choose? Well, the nice thing here, guys, there's tons of information on these and what they do in the help file and various blogs, but no matter the solver, they should all get to the same result. Some of them can just be much quicker depending on the problem. So the easiest thing to do is use the automatic solver selection option. Based on your setup, the number of contact sets, the total degrees of freedom of the model, things like that, SOLIDWORKS is going to pick the solver it thinks will work best. And for new users, that's definitely the best option. So that's all I'm going to check here. When I go into my study properties, again, just right-click properties, I'm going to make sure automatic solver selection is turned on. And again, lots of other options here. We cover all of these in our training courses, both online and in the classroom. But for an initial study, if you're setting automatic solver selection, that's really all you need to turn on there. So what do we do now? We've worked that tree from the top to bottom. We have a meshed model. Well, it's time to run this. We're going to go up. We're going to click that run button. You'll see the solver window pop up. Sometimes it's quick, sometimes it's a little bit longer, but you'll see it goes in and it's created, or it's ran the study and showing me a result on this. Well, the first thing I'm going to do, guys, I'm actually going to hide all my symbols here. My restraints and my loads, they make it a little hard to see the model. Easy to do. Right-click my fixtures, hide all. Right-click my loads, hide all. What's the next thing we should do with results? Well, we should animate this plot. And why? Well, I'm going to click the animate button. The default is just a 5-frame animation. That can be a little choppy. So I usually like to stop this and I'll reset it to 15 frames and play it again. Now, this looks like it's doing what we want it to. And that's the whole point of this animation. And that first check is a gut check. If I found out only one of these sides was moving or it was flexing into or out of the screen, something like that, unintended behavior, well, I know I have a problem. And there's no point digging into the results further until I fix it. But as a gut check, I go, yeah, I put 300 pounds on these. It's flexing downwards. It's developing some stress. It's basically doing what I think it should do. So things are correct. Now, you might look at this and go, that's flexing a lot for a 6061 aluminum part with 300 pounds on each side. Well, typically with metal parts, these deformations are going to be small enough that you can't really see them with the naked eye, or at least not easily. So what SOLIDWORKS does, it exaggerates these. And you'll see it right up at the top of my plot, this deformation scale here. Now, that's 105 times the actual deformation that my part is seeing. It's flexing 100 times more in the picture than it would in real life, but I now get to see the mode of flexing and where that flexing is actually taking place Now, when it comes to results, we're going to talk about three things, guys, or a couple things actually. Plots to start with. What are these default images that I see? What can I do with them? And then how do I know if my part is actually refined enough? So to start with, we have three default plots. We have a stress plot showing von Mises stress. We have a displacement plot showing how far this part is deforming. And we have a strain plot. Well, I'm going to focus on stress and displacement for now. The stress plot is actually showing me where my high stress areas are in the model. And the highest stress in this model is 37.1 right now. And we'll actually see it happening right here. I'm going to guess that's on the upper surface, but is it on the upper or lower? Which is it? Well, a really useful feature is having SOLIDWORKS tell you where the highest stress is. If I just double click on my color bar here, very first option that comes up here, show min and show max. I'm going to show the max annotation. It's now showing me where that maximum stress value is. It's on the top face right there, 37.1. Well, down at the bottom, you'll see this material yields at 55.1 next to this little arrow. So I'm yielding yet, I'm safe, but if you ever are above yield, you're going to see this arrow show up somewhere in your tree. So if it was showing right here on the green level, anything above that arrow would be yielding in this case. So 37 MPa, 55 MPa is my yield strength. I can actually run a quick safety factor check on this if I'd like to. And what I'll do, I'm going to go 55.1 divided by 37.1. I have a safety factor of about 1.5 on this, 1.48 right now. But we'll actually see in a moment, SOLIDWORKS has an easier way to do that as well. So what I can do, let's talk about safety factor in a moment. Let's jump to displacement. How far is this actually flexing? Well, if I double click my displacement plot, it's going to show me in millimeters. And this makes sense. The part that's moving the least, well, this whole center column is pretty much at 0 millimeters displacement. The parts that move the most are on the outside. And again, it's clear in this case, but if I want SOLIDWORKS to tell me where the maximum displacement is, double click the color bar, show max. There we go, 0.02 or 0.2 millimeters right at the tip. So again, if that was really flexing 0.2 millimeters, we wouldn't be able to see it as well. That's why the deformation scale is here. So what else can we do with these plots? I'll show you how to create a one quick plot, which is a safety factor plot, and then we'll talk about sorting through these. So I'm going to go to my results folder, and I'm going to right-click and go to define factor of safety plot. So you'll see there are other options. We just don't have time to cover them today, strain plots, new stress plots, etc. I'll go to a factor of safety plot. I'm going to leave it on the automatic settings right now. And what I do when I click through this, this multiplication factor, by the way, just lets you scale the results. I'm not going to do that. But I can have it show me a factor of safety distribution or just flag areas below a certain safety factor. So if I was shooting for a safety factor of, let's say, 3 in here, I can do that. And you'll notice before I even click OK, it's telling me my minimum safety factor is exactly what I'd calculated there, about 1.48, 1.5. So I click OK. These are the areas of the model where my safety factor is less than 3. Anything that's in blue right now is a safety factor above 3. So I can very quickly find out where I may need to modify this model. But let's go back and talk stress for another moment. I'm jumping back to my stress plot. Now, one thing you guys may notice in here, these results look a little bit jagged. And how do we trust this number, this 37.1 number? Well, really, on your first run, whenever you do a first mesh, you can't trust that number. We don't know if that's 37 or if we'd refined the mesh in here, basically. You can think of it like giving the model more resolution in those high stress areas. The stress could change. As we add more elements, we might actually find out that it's 47 or 57, something like that. We don't know until we try refining the mesh. Now, when we refine the mesh, I could go back to my default mesh in here and try and recreate it and use this slider bar again. But what I'm going to do, I'm just going to tweak something here, guys. Instead of actually doing that, I'm going to go in and show you guys another way to do it. I can refine mesh. Let me go back and I'll actually do that at a more fine size so these are easier to see. Now, when I do something like this, if I'd like to refine the mesh just in those high stress areas, which is kind of this fillet, and the bottom face, I don't need to dial down the mesh everywhere. I can do what we call a mesh control. I can right-click the mesh folder, say apply a mesh control, and what I can do here is pick where I'd like to refine the mesh, and I can define how large I'd like those elements to be. So maybe on those faces, I'm going to use 1.5 millimeter elements, and what you'll see underneath this is what we call a growth ratio, but leave it at the default. That's fine. So when I click OK, it doesn't look like it changed, but I see these pink dots everywhere. This is just given an instruction to the mesher to control the mesh, but you'll see the little warning symbol next to my folder here. It doesn't actually happen until I mesh it again. So when I go and mesh it again, this is a much, much finer mesh on those regions. So I'm going to run it again. And remember, we were at about 37.1 MPa before. When we run this, and it's going to take a little bit longer to solve this time because we do have more elements in there. It's a more complex calculation, but still going to solve pretty quickly. You'll notice these stress contours look a lot smoother than they did in the high stress regions here and along the bottom. Much smoother contours. That's what we're looking for. But really what we're looking for is the number up here. I just made the mesh much finer on the top surface and the bottom surface there, my high stress zones, and my stress changed from 37.1 to 37.5. Now, I could try one more mesh on here if I'd like to, and run this with a slightly finer mesh to see if it's going to change, but it's probably not going to change much in here. If it jumped from 37 to 47, well, I'd want to keep going, but we just saw a like 1% change in the stress, so I'm okay with that. We can assume this is actually good. Now, things we can do with the plots, and it looks like we're a little over time here, guys. I've got about 5 more minutes left, and I think it's pretty useful stuff. If you guys can stick around for the next 5 minutes, I think it'll be worth your while. So let's actually look at plot tools for a moment. We've talked about how to sort of view these different plots, stress, displacement, then we showed that factor of safety plot we created before in there. But what else can we do with these? Well, to start with, these pink dots are getting annoying. I might hide these. When I go to my mesh control, just right-click it and say hide. Gets rid of the symbols. Well, in my plot tools folder, I have various different options here, and one of the most useful ones is probe. So if I turn on my probe tool, this is going to let me basically ask SOLIDWORKS what stress is anywhere on the model. So with my color bar here, if I want to see the stress right in the middle of this fillet, right where my mouse cursor is, it'd go, well, it's kind of yellow-ish, verging on green. It's probably, I don't know, between 25 and 28 MPa. Well, you can do that, or I could start my probe tool and just click right there. Well, it's 25.3. Up here, it's 2. Up here, it's 2. Down here, it's 36.9, etc. And this is actually nice because you can rearrange all of these probes however you'd like it, including the maximum that comes up automatically there. Take a screenshot of the model. Use the Windows snipping tool or print screen, whatever you want to do, and use this for reports. And by the way, the color bar also moves. If I want to move the color bar around to take a better screenshot, I can move it from the left to the right, etc., just by dragging. Now, I'll close the probe tool down. When I close it down, all my probes disappear. But there is another thing I can show you here, and let me do this probe one more time. If I would like to probe along a certain edge, so let's say instead of just at certain points, I want to see how the stress varies along this fillet from the top to the bottom or bottom to top. Now, instead of just picking a point like this, I can go over, instead of probing at location, I'll probe on selected entities. And I can now pick faces or edges. If I pick a face and click update, well, it actually grabs every single node on that face, and it's a ton of data. But the neat thing, it's going to show me averages. Average stress on that face is 17 MPa. Well, edges get even neater, because if I go in and I probe that edge, I'll just click the update button, it does grab every single node along that edge, and that's too much data to work with. But if you go down and click the graph tool where it says plot here, it's going to show me a stress plot, how that stress changes point to point. We're actually looking at it, it's more like this. Guys, if I graph it, it's going from left to right. We see at the bottom of that edge, it starts at kind of a yellow mid-stress, very quickly peaks at the red stress there, and then it's going down, and by the time we get into the vertical sections, it's very, very low, near zero. So these can be your best friend in terms of understanding how stress is varying. I can also save this out to an Excel file, do all my own post-processing in Excel. So some other things we can do. Section views to see what's inside the part. Now, my normal section view tool, even if I go in and spend a lot of time setting up a section right through the part, nothing happens. It uses a different graphics engine than SOLIDWORKS does, so this section view tool actually won't work. What I need is under plot tools what we call section clipping. Now, with section clipping, this is a section view specific to simulation. So I can choose a plane, choose my clipping direction, etc. And I can physically push this through the part to wherever I'd like to see it. And I can even do things like showing the mesh on the section plane to see what the mesh looks like, what my element density is like, etc. So let me shut it down. There we go. That's some really basic result dealing on a plot like in a study like this. We've talked about the different things we can do. There is more, and I'd encourage you to kind of explore it, guys. The final thing that's nice, there's a report option, and what this is going to do. Oh, I have apparently an installation issue with Microsoft Word. Normally, what that does is it'll give you a nice little canned report. Not something I'd hand into a client or a boss, but what it is good for is logging all of your settings. It's going to take a bunch of screenshots of your model, capture exactly what was set up, what all your settings were for the mesh and boundary conditions and things. So it's a great log of basically, what did I do there? If you ever have to look back on something in 6 months and remember how you set it up, the report's going to be your best friend. So one final thing we're going to go through today, guys, and we've talked about the plots, we've talked about the probe tools. I'd like to talk about contact a little bit. So what if we have, let me shut this down, what if we have two parts? Something like this, and I've got my bracket, and I also have a pin that's going through the bracket. If I look at my contact here, the underside of the pin is actually contacting in here, but it is not, we're not contacting on the shank. Now, what I'd like to do here is actually pull this pin outwards and while fixing the bracket and see how this part actually reacts. Well, when I go in and start a new study, we're going to use the exact same setup we did last time. You'll see me breeze through it a bit here. I'm going to apply just a default material, we'll say a steel in here. But now under connections, I see some stuff. Component contacts. Well, we see what we call a global bonded contact here, and I'm going to edit that. What that means, that global bonded contact, globally, it's set to bonded. So anywhere that pieces are touching, like the underside of my head in there, SOLIDWORKS is going to bond it together. Now, that might not be what we want. In this case, I don't want the head bonded onto the bracket. I actually want it to be able to sort of slide around and develop some friction and a contact patch in there. So if I want those parts to actually behave realistically and contact each other rather than being bonded, I'm going to set it to no penetration. Now, just as another example, if I went bonded contact here, as I mentioned, it's going to bond all of the touching faces. So it's not really like we have a peg in a hole. It's more like we've machined this big funny looking bracket and a pin all as one piece out of one block of metal on a CNC machine. So I'm going to set my global contact to no penetration. That's going to make these parts actually behave realistically to each other. And I'll go in and start setting some options here. I'll go into my fixtures. I'm going to fix these two faces. I'm going to go to my loads. I'm going to apply a force here, pulling this outwards. So I'll reverse it. And we'll use, I don't know, maybe 200 pounds. Okay. So I'll use a default mesh. Again, I'm going to, just like I did the first time, go to a curvature or the blended curvature based and just let it run with the defaults for a first try. Like that. Well, the setup steps are exactly the same with assemblies, except you have to worry about this contact. So we'll run it one last time here. You'll notice the solution takes quite a bit longer too, and whenever it sort of stops like this, let me do that one more time. When it stops, if I pop open the little more option, you'll see what it's waiting on is solving the contact. Solving contact constraints is what takes the longest amount of time. Now, Show you another neat thing here. When I use no penetration contact, my default deformation scale goes to 0. So it actually shows me true deformation. It's really hard to see what's going on in here. So if we want to change that, I can. I'm going to edit my stress plot. I'll just right-click on it and say Edit Definition. Well, here's where SOLIDWORKS actually chooses how much it's exaggerating the deformation. And I'm going to go up to Automatic here. It's telling me that's about 1,000 times exaggerated deformation. That's what it looks like. Well, that's a little bit messy to see. So let me maybe bump that down. If that was 1,000, let's try about 200. You know what? I might do that a little bit more. Let's go up to 400. All right. Next step, same as it was last time, we're going to animate this plot. So as I go through and animate it, I can see what's happening. This is stretching, pulling outwards like that. And another neat thing with assembly is if I want to see what's happening inside the contact patch there, I can actually do it, but I need to hide one of my parts. So how will I do that? I'm going to go back to my model. Let's say hide the pin for a second. I'll take the pin and say hide. Then if I go back to my study and show the stress result, well, it's going to hide that pin. And we'll be able to see what the contact patch looks like in there. And I can animate this. I can do any sorts of stresses I'd like to. I'm going to show you one last thing, guys, really quickly, what we call a contact pressure plot. This is a new stress plot. Just like I could define a safety factor plot, go into a define stress plot. I'm going to change my stress quantity here down to contact pressure because I'm looking for what's the actual stress between the underside of that head and this bracket. So when I do that, it's going to show me this contact pressure. And what that's doing, you know what, a better way to show this might be, let's show the pin and hide the bracket, and we'll look at these results on the pin instead. That's better. That's an example of what the contact pressure looks like on the underside of the pin head in there. So I can see the highest stresses at the top and the bottom. Got about 40 MPa of contact pressure in there. And towards the middle, well, we have very little contact pressure. And why is that? Well, you can think this part is actually bowing outwards a little bit. If I were to draw the bracket right now, just let me grab my pen. Well, the face of the bracket that may have started flat, well, it's going to be slightly bowing outwards like that. So the majority of my contact is happening at the bottom and the top. Those middle faces, very, very little, pretty much negligible contact. So hopefully, guys, this has given you a good, at least first glance look at simulation and enough to get started and start trying it out on your own. Again, it's not this is no replacement for simulation training. I would highly recommend you take some of the Javelin simulation training if this is something you guys want to get into. But this is enough to hopefully get you started. Start trying things out on your own parts. And if you have any questions, please let us know. Call the Javelin Tech Support line or call me directly, email me directly. I'm always happy to help customers work through their issues on this.